Good morning, students. Today we are going to discuss very important topic from chapter 7, AC source with LCR circuit. So what we have taken, inductor, capacitor and resistor, and we have connected these component in series, and across the series combination we have connected an AC source, and the AC source is your V equal to V naught sine omega t. Now already we have discussed AC source across inductor, AC source across capacitor and AC source across resistor, and independently we have defined potential and current. Now the equation which we have defined before is your the AC source is your V equal to V naught sine omega t, and AC source across resistor, the current equation is your I suffix R I naught sine omega t. R is your resistor, I suffix L for inductor, I naught sine omega t minus pi by 2, and I suffix C, I naught sine omega t plus pi by 2. And from Ohm's law, V suffix R, R, I suffix R, V suffix L, XL, IL, XL equal to omega L, and V suffix C, XC, IC, XC equal to 1 by omega C. So XL and XC are the resistive part for inductor and capacitor. Now we have seen that in case of resistor, current and potential is in same phase. That's why we have represented VR and I along x-axis. Now if we consider current, I is the current I is the current in a AC source with inductor, then the equation already we have defined is your current is lagging that of potential by pi by 2. So potential should be along y-axis, then current and potential will be lagging behind, or you can say the current is lagging behind by pi by 2 with respect to the potential. Similarly, in case of capacitor, current is leading pi by 2. So that's why V suffix C is in negative y-axis and I is along x-axis. But this is your phasor diagram. So phasor diagram is nothing but a vector diagram. So what we have done, we have taken the magnitude VC, V suffix C from negative y-axis, and we have superimposed over the V suffix L. So as a result, what will happen? The resultant part is your VL minus VC. Now if we consider this rectangle part, so this rectangle is your one side is your VL minus VC and another side is your V suffix R. So if we consider the resultant part is your V, and this is nothing but the diagonal because it's from the vector law addition. So if we consider the right angle triangle, then one side perpendicular is your VL minus VC and hypotenuse is your V and base is your V suffix R. So if we apply Pythagoras theorem, it should be your V square equal to VL minus VC whole square plus VR square. So V is your root over VL minus VC whole square plus V suffix R square. Now V is the resultant potential. So as per the Ohm's law, Z is nothing but the resultant resistive part in an LCR circuit, and we define that Z is your impedance. The resistive part we define as a whole is the impedance of the LCR circuit. So we have substituted the V suffix L as per from here XL I, or as we have considered I here in the diagram. That's why we have considered I instead of I suffix L, just to denote that I suffix L is the current through the inductor. We have written I suffix L. Otherwise in the figure we have given I. That's why we have simplified here. That is your V equal to IZ IXL minus IXC whole square plus I square R square. So you can take out I throughout. So what remain? XL minus XC whole square plus R square. So Z is nothing but the impedance of LCR circuit. Now you can define if I is the angle made by the resultant V with respect to the current axis, then tan phi is your VL minus VC by VR, perpendicular by base. So you can write IXL minus IXC by IR. So I goes off, so XL minus XC by R. So phi equal to tan inverse of XL minus XC by R. So phi is nothing but the phase of LCR circuit. Now we will consider this part. This part is very important. Now if we consider XL equal to XC or XC equal to XL, so in place of XC we have written 1 by omega C. Already we have defined here inductive or capacitive reactance, and XL is your omega L, inductive reactance. So omega square 1 by LC, omega equal to 1 by root over LC. So omega is your 2 pi nu. So nu equal to 1 by 2 pi root over LC. So this is nothing but the resonance frequency of the LCR circuit. So if this condition satisfy, then Z is nothing but is your R. So you can say the circuit is purely resistive circuit under this condition. Okay. So this part is very important for the numerical. In exam it is asked to define the resonance frequency. So you have to use this equation directly, nu equal to 1 by 2 pi root over LC. Now further you can define cos phi. Cos phi is your base by hypotenuse. So it's your VR by V. VR is your IR and V is your IZ. II goes up R by Z. So cos phi is known as power factor of the circuit. And sin phi perpendicular by hypotenuse. So VL minus VC by V. So it comes out to be XL minus XC by R. Now we are trying this numerical. A 40 ohm resistor, 3 millihenry inductor and a 2 microfarad capacitor is connected in series to a 110 volt 5000 Hz AC. Calculate the impedance in the circuit. So R is your 40 ohm, L is your 3 millihenry, C is your millihenry means 3 into 10 to the minus 3 henry, and C is your 2 microfarad, 2 into 10 to the minus 6 farad. So what we have do, we have calculated XL, L omega. L is your given 3 into 10 to the minus 3, omega is your 2 pi nu, 2 into 3.14, nu is your 5000. So you can calculate, it comes out to be 94.2, and XC is your 1 by omega C. So 1 by omega is your 2 pi nu, 2 into 3.14 into 5000, and C is your 2 into 10 to the power minus 6. So if you substitute, you will get 15.92 ohm, and if you substitute this value in the formula Z, that is your XL minus XC whole square plus R square, and then you probably will get 88 ohm. So check this calculation by yourself and try to find out the result. So this part is very important from the numerical point of view. So this is all about. Let me repeat this phasor diagram once again. So as already we have defined AC source across inductor, capacitor and resistor, and we have seen that in case of resistor both are in phase, and in case of inductor current is lagging by pi by 2 with respect to the potential. So that's why I is along x-axis and VL is along y-axis, because current is lagging by pi by 2. Now in case of capacitor, current is leading by pi by 2, that's why it is along negative y-axis, and as it is a phasor diagram, these are the vector parts. So we have superimposed VC over VL, and resultant part is your VL minus VC. So if we consider VR and VL minus VC as the two sides of the rectangle, then resultant part is your V, which is nothing but the diagonal of the rectangle, and from here we can calculate the rest parameter. So this is all about. Please go through this one and try to find out your doubts. Thank you.